I'm going to be giving a talk complementary to Athena's regarding its work regarding the SERRANO project, and I'm going to be speaking to you about our efforts in interoperable execution and application deployment with hardware acceleration. I will be focusing on serverless computing, well, in the sense that our main motivation for doing this work has been serverless computing and the challenges we have regarding hardware acceleration in this paradigm. So a brief introduction about serverless. It is an upcoming programming computing paradigm in which the user of the infrastructure does not need to manage any of the underlying infrastructure. They just want to deploy their logic somewhere in the platforms provided by the owner of the infrastructure, and this is going to be done without having to configure any kind of resources. That could be hardware, VMs, Docker containers, Kubernetes clusters, etc. A particular case application of serverless computing is what has been called function as a service. In this model, users deploy code, just code in the provider. For example, they develop their logic in the form of functions, which are then deployed in the platform in the service that the user is using. And these functions are meant to be short-lived. They have no state, and they are triggered by events. The great thing about that is that your code is being live only when you need it because of the event-driven nature of this. And the good thing as well from the customer's point of view in this scenario is that you are being charged only for that. In comparison, when you deploy an EC2 VM on AWS, you are charged for as long as your EC2 VM is up. Or when you deploy a cluster, a Kubernetes cluster, that holds as well. With functions, you just get billed for the time your function has been executing. Okay, so what is the problem of FAS in the context of hardware acceleration? Here is a typical very high-level overview of how AWS Lambda probably looks like. So there is Amazon, who owns some sort of hardware which might have one or more GPUs or other kind of hardware accelerator. The user provides a function to be executed in the AWS Lambda UI. And what Amazon does is that it packs this function inside a container, and it launches that container inside the VM. The reason why they use VMs is because this is a multi-tenant environment. They care about isolation between users. They do not want they want to restrict the resources users are using, and potentially malicious users being able to access data of their co-tenants, right? And the problem with that setup is that at the moment in AWS Lambda, these hardware accelerators do not get exposed inside the VMs. And the reasons for that is that it is quite hard to expose hardware acceleration inside VMs, especially in the context of multi-tenancy. It is very hard it is an open problem, in fact, on how you can give access to that function, the code running inside the VM, to the GPU down there in the hardware. So there are multiple ways to tackle this problem. But first, let's see what this means. So when you want to deploy, for example, let's say a machine learning workflow, for example, here we deployed on AWS Lambda an inference workload with TensorFlow. I think that was a ResNet 50 model in this particular case, and we started sending requests for classification, for image classification on that function, and we started playing with a number of requests to see what kind of throughput we can get from this deployed function. And you see that the throughput we achieved plateaus at some point in something like 3.5 functions, image classifications per second. Now we all know that machine learning heavily makes use of hardware acceleration, and in fact, if you run the same exact code on any laptop that has a GPU, and you repeat the same experiment, that is what you would get, and in fact is very close to what TensorFlow public charts tell you that you can get as performance from that particular model. So our proposal to tackle this problem is essentially a framework that exposes inside VMs hardware acceleratable functions in a portable way, in the sense that you can take your code, deploy it in a VM or anywhere else without having to modify the code. It is secure in the sense that we can do that inside the VM, right? And the core concept here is that the framework is hardware agnostic. So the API we give to the users, to the developers, is hardware agnostic. It has nothing to do with the intrinsics of CUDA, OpenCL, or any other low-level framework. In fact, the core, this is the high-level design of the core component of our framework. It is a runtime which exposes a number of functions to the programmer. The yellow box here, it is a core runtime. It is a dynamic library. Okay, and these functions on the top are the ones that we promise to the user that they can be accelerated. Okay, so the user does not need to write hardware-specific code with VXL. They consume the API of VXL, and VXL itself, it employs a pluggable design where the hardware implementation of those functions on the top are provided through plugins to the runtime that are being loaded at runtime when you deploy your code, depending on the available hardware you have. So for example, if you are running a machine with a GPU, you could load the TensorFlow plugin on the back end, which knows how to execute your image classification code on the top. But and in the case, for example, that you are running a machine that you have a very nice TPU that can further accelerate that, you could load that plugin in order to be able to speak with a particular hardware device that does that for you. The important thing here is that the yellow box, and as a consequence, the user application is not hardware specific. So when you build your application using VXL, you can migrate it from machine to machine without recompilation, relinking, or rewriting. And you can deploy it in that other machine just by loading the proper hardware plugin. So we can see that here. So a typical machine learning application would have a core of, would be a binary that consumes, for example, a TPU library interface, and like that, it's able to run a hardware that provides a TPU accelerator and accelerate these operations. In this case, the TPU-specific code is part of the application itself, right? So if you want to take that application and execute it in another machine where you have a GPU, you cannot. You need to rewrite it, recompile it, relink it, or what you have. So in contrast with VXL, the application would look like that. The application would consume the machine learning API of VXL on the top. This is hardware agnostic. And when you are about to execute on a machine with a TPU accelerator, you would load the TPU plugin. Now, if you migrate your application to another machine, or you scale out your application in another machine that has another kind of device for acceleration, you can do that by loading just another plugin and get your performance characteristics that you actually expect. Now, what is the story about VMs? For exposing this inside the VM, VXL follows a API remoting approach. So essentially, the API of VXL, it gets serializable over a transport layer, and like that, we can offload requests for acceleration from inside the VM down to the host, where we have an entity which actually has direct access to the hardware acceleration, and it runs your requests on that hardware for you. So in this case, we have a BLAS application. As an example, it consumes the relevant API of the VXL runtime. And the plugin that we are using inside the VM is a special transport plugin. Our transport at the moment is based on Virt.io. Virt.io, and in particular VSOC. VSOC is a para-virtual interface that allows communication between guests and hosts, the guests and the host they're running on. So we serialize the requests for acceleration for doing matrix-matrix multiplication, for example, over the vhost transport. And on the host, there is essentially a VXL application that is listening for requests, deserializing those requests, and executing them on the available hardware. Okay? The difference between other API remoting approaches here is that essentially the granularity on which we operate. We control the API we provide to the users, and we do not directly need to speak with the driver and intercept requests to the low-level CUDA driver, for example, which has been shown to have latency issues, and its main problem is that it is hardware specific, right? So we can break this problem by defining our own API, which is hardware agnostic. So we do all that, we said, having serverless in mind. So in this context, in a serverless execution scenario, you would have your functions being deployed through the UI of the FAS system, and the functions would be deployed inside Firecracker VMs or any other VMs. VSOC is a standard transport, so we could have any other VM here. And they would be deployed on the platform. Those functions are able to speak with the agent running on the host and get the acceleration requests, their acceleration requests handled by that agent. The agent here is able to multiplex requests for multiple tenants. And in fact, it is the point in which we're trying to as well enforce quality of service requests, quality of service promises, or SLAs from the user. Now, we do not have access to AWS infrastructure, so we replicate their setup by using Kata containers. Kata containers is a very interesting project that essentially it allows you to deploy workloads. I'm sorry. It allows you to deploy workloads, containerized Docker containers or CI containers, where they are deployed inside VMs. They're packed inside VMs, so you can get these nice isolation characteristics. And in our case, we play mainly with Firecracker because of the ultra low, small boot time properties it provides us. So we have an alpha implementation of this. The implementation, we are using and experimenting with that. We support the TensorFlow API for running inference, essentially, and BLAS operations. There are language bindings for Rust and Python for the VXL API. And as well, we are working on integrating the API with higher level frameworks such as TensorFlow so that we can port applications on VXL without having to change applications. This effort is essentially allows users to get an existing TensorFlow application and deploy it without having to change it to the VXL framework. And we work a lot with community projects such as Kata Container, Firecracker, and we integrate all this with Kubernetes, which is our orchestrator. It is what allows us to deploy workloads on our cluster. And we use OpenFAS as the front end for having FAS semantics. And finally, we experiment with unikernels as an alternative way to isolate workloads. Yeah, that's just a summary. We have been speaking about our work on SERRANO regarding hardware acceleration in virtualized multi-tenant environments. We presented VXL, which allows us to do this in a portable and secure way, and how we integrate this with other community projects. And we plan to extend our API in the following weeks, months, and the hardware we support, as well as the integration with higher level frameworks, and doing some research in what sort of semantics we can put in the runtime for doing more intelligent, taking more intelligent decisions regarding scheduling of resources and so on. I think I'm well out of time, so thanks. Thank you.